Now we will solve some decidability problems. Given a Turing machine which has at least 481 states, is it decidable or not? Sir, what is the meaning of decidable or undecidable? Already I told you, you have a property, let's say, forget about these problems first. You have a property called P, right? Now, this is your bag. In the world, there are infinite strings, correct? We know that. Any string satisfies a property, such string we write in this bag. Okay, so this is a property bag, I can say. Now we are filling all the strings which satisfies the property, right? So that forms a language. Now you can easily understand the relationship between property and a language. Language is nothing but a collection of strings which satisfy some common property. Now here also we are going to, now forget about that first. Now we have a language. A language is decidable when it has a recursive it has a recursive Turing machine, otherwise total Turing machine. We know that, right? If there is no total Turing machine for any problem, then we say it is undecidable. Okay, remember it. Now I am going to design a total Turing machine for every problem here. Okay, sir, we understand this concept. You have a language. Finally, if that language has a total Turing machine, it is decidable, otherwise undecidable. But here I am not seeing any language. You see, what is the corresponding language here? Given a Turing machine has at least 481 states, is it a problem? Yes, it's a problem. Is it a property? Is there any property? Yes. So in the world there are infinite Turing machines. Turing machine 1, Turing machine 2, Turing machine 3, so on. Okay, so given a Turing machine code, maybe it is valid code or invalid code, I don't know. Then collect all the codes like M1, M3, M5 which have at least 481 states. Example, M1 and M5 and M3 are the Turing machine codes which have at least 481 states. Okay, 487, 534, in that way. These are the number of states. Let me collect that kind of Turing machine codes. So here again it's a property, right? Now this property is giving you a language. So here language is nothing but collection of Turing machine codes which have at least 481 states. Now such language is decidable or undecidable is the question. Now slowly you understand that problem can be converted into a language, correct? So here problem is whether a Turing machine has at least 481 states, and the language form for that is nothing but collection of Turing machines which have this property. Such language is decidable or undecidable. Now we know the definition of decidability. Given a language, whether it is decidable or not, how to check? For that we have to construct a total Turing machine. The total Turing machine should do this one. So for that we will be giving a Turing machine code. If really that Turing machine satisfies this property, means the Turing machine has more than or equal to 481 states, it should say yes, otherwise it should say no. Such Turing machine, if you design total Turing machine, then we say that this Turing machine problem, that means given a Turing machine has at least 481 states, such problem is decidable. Okay, now finally this is very important. I have to show you a total Turing machine. For that, Turing machine code is given as the input. Then that total Turing machine should tell whether this Turing machine M has at least 481 states or not. That is the relationship between this problem and a language problem. Understand? Now ask yourself, how can we try to develop the intuition? So how can you say that a Turing machine has at least 481 states? If I give you a Turing machine code, forget about this machine. Let's say as a human being, you tell me how you decide whether a Turing machine has 481 states. Let's say you are a human being. I will give you code of Turing machine. Then how you decide? Simple, sir. I will see the description of the Turing machine. In that, number of states will be mentioned, correct? What is the definition of Turing machine? Turing machine is a 9 tuple, and that number of states will be mentioned. Number of start symbol will be mentioned, final state is mentioned, transition function is mentioned, right? I read it. After reading it, I will realize how many states that Turing machine has, correct? So in that way, so easily we can decide it. That means as a human being, easily I can check whether a Turing machine has 481 states or less or more. But how to construct a total Turing machine? Whatever the logic you developed in your brain related to this problem, For that we can construct a total Turing machine. How you see? Now we'll come to the construction part. Already we answered using intuition, because as a human being you said that by reading the code, by counting the number of states in the description, we can get it the number of states in the Turing machine, right? Exactly the same thing we can do with the code also. Now we are going to construct a total Turing machine for that. Okay, this is your total Turing machine and let's call it as n. Okay, remember it is a total Turing machine. Input will be some Turing machine code, because we know the language which we are going to accept. Our language which we are going to accept is nothing but collection of Turing machine codes, where the Turing machine codes are having at least 481 states. For that what you do is take an encoding of Turing machine as input, copy that into one of the tracks. Let's say I am copying it here. After that, through my code, that means your total Turing machine's code will be such a way that it will scan the code of M. Okay, we can scan it. Did you remember? Already we have designed 2-3 Turing machines. Then you understood that we can copy code from one place to another place, and we can identify some patterns also, correct? And that's why easily we can go to the position where the number of states is mentioned. Okay, did you remember Turing machine encodings? In Turing machine encodings, I told you that. So it will be like this: 0 power 71, 0 power 23, in that way. So here this pattern, first zeros. Before this first one, the number of zeros represents number of states. In that way, there will be one description, correct? So based on that, easily by scanning this Turing machine code M, then I will know that the number of states in this Turing machine. If it is 75, then definitely number of is this Turing machine has at least 481 states? No, only 75. Then I will reject. If it has more than or equal to 481 states in this Turing machine M, then I accept. Now you get confidence that we can design a Turing machine, total Turing machine. Here, do we require to loop on anything? Unnecessary, correct? So that's why we can happily design a Turing machine which is total Turing machine, correct? For this problem. That's why this problem is decidable. In simple words, because just scan using your total Turing machine, scan the input and identify the number of states in that Turing machine, because we have a description of that. Then based on that description, just decide whether it has more than 481 states or less than 481 states. Based on that, always I can say yes or no. That means always I can decide whether it has 481 states or not, correct? No looping is required. That's why it's a total Turing machine. Now we'll see second one. So is there any Turing machine? Given a Turing machine which takes more than 481 steps on input epsilon. Now this time language is like this: collection of strings M1, M2, M3. What kind of Turing machines codes we have to collect in our language? Problem B is a language. Okay, what is that language? It's a collection of Turing machines which take more than 481 steps on input epsilon. So example, let's take an interview of some Turing machine M5. Mr. M5, if I run you on epsilon input, how many steps you take? 75. Oh, then you don't take more than 481? Yes, I don't take more than 481. Then don't collect it. If you do that, then you will form some collection. That collection is a language. Now the question is, that language is decidable or not? This problem and this language are same. Okay, so it is a problem form, this is language form, both are same. Try to understand the relation between them. Now such language is decidable, then we say this problem is decidable. Now you tell me, given a Turing machine code, can we tell whether it takes more than 481 steps on input epsilon? Such a Turing machine is possible? Yes, possible. How I am going to design, you see. First of all, I will try to develop a intuition. As a human being, how you answer it? Example, I will give you Turing machine code. Read it. Okay, so given a Turing machine code, number of states, everything, then how you know whether that takes more than 481 steps on input epsilon? Simple, sir. Definitely by seeing the code I can't say, but I have to run that code on epsilon. I will run that code on epsilon and I will count the number of steps. If it takes more than 481 steps, then I can decide. Now let me ask you a question. In this process, do you really require to go to infinite loop? No, because every step we can easily count. That means after 482 steps we can decide everything. we don't really require arbitrary number of steps, correct? So that's why, so my intuition says that this problem is decidable, because just run your Turing machine for 481 steps. If within 481 steps, if it the question is, will it take more than 481 steps or not? Okay, run for 482 steps. If run for 481 steps first. In these 481 steps, if it won't accept, then definitely I can say that it takes more than 481 steps. That means in that step, number of steps itself, it should go to final state. Sir, I ran my Turing machine for 481 steps, but still I did not go to T state or R state. Okay, then that means what? It is going to take more number of steps. Then we can easily decide, correct? So finally it is decidable problem. Now let me give the description of that. I am going to construct a total Turing machine like this. Given a Turing machine code M, I will copy that into one of the track, okay, so that I can simulate it. Now using my finite control, because I know the problem, that's why I can customize my design. So my design will be like this. Using my code, that means let's say this is Kiran's Turing machine, which is total Turing machine. Don't get confused between M and Kiran's Turing machine. M is a Turing machine on which we are solving this problem. Given a Turing machine M which takes more than 481 steps or not. For that I am designing a total Turing machine to answer that question. That is Kiran's Turing machine. How it works, you see. Kiran's Turing machine will have a code such a way that the code will do, first of all, it will copy that input M here and it will generate epsilon. Yes, using a Turing machine, easily we can generate a string epsilon, correct? It's not a big deal. You also can do that. It's homework for you. So what you have to do is, you have to write epsilon on tape. If you write it, then that automatically it means you are generating epsilon. It's a big deal? No, it's not a big deal. So finally M epsilon. After that I simulate, because we know that how to simulate a Turing machine on an input. So simulate this Turing machine M on epsilon. That means Kiran's Turing machine should do whatever M is doing on epsilon, because we have a code for it. Already I told you. That's why this time I don't want to discuss, directly I tell you. So because we have a code of M, then we can run that code on epsilon. How many steps you run? Every time when one step of this Turing machine is executed, count it. Okay, so take another tape. Here you maintain the count. Yes, it is possible. Then in that way, every time once one step of this Turing machine is executed, count it. In that way, count the number of steps which you execute and run for 481 steps. After 481 steps, still this Turing machine M did not go to final state. That means what? I can say that this Turing machine M which you are simulating, that takes more than 481 steps on epsilon. That's easy. Sir, after 70 steps directly it went to final state. That means what? It won't take more than 481 steps. In that way always we can decide about it. That's why this problem is decidable. We can have a total Turing machine. In this process, Kiran's Turing machine, which is a total Turing machine, is going to accept and reject, but it never needs to go to infinite loop, correct? Why I have to go to infinite loop? I simply simulate this Turing machine for 481 steps and I decide always. That's why there is no looping. Now we will see one more problem. That is statement C. Takes more than 481 steps on some input, not epsilon, some input. That is a trick here. Sir, how do we check on some input? Because there are infinite inputs possible, correct? On which you will decide, on which you run. I will tell you, don't worry. So here you think that this is undecidable problem. Why? I will tell you. Sir, actually a Turing machine takes more than 481 steps on some input or not, but some means any input, right? Then I can't decide anything by only checking only epsilon, sir, correct? Yes, because infinite strings are possible, epsilon, 0, 1. This question is about all possible inputs. Epsilon 0, 1, 0, 0, 0, 1, 1, 0. In that way there are infinite strings, correct? Now example, as a human being, if I take a Turing machine and if I run on that epsilon for some 70 steps, let's say. After 70 steps, let's say this Turing machine halts on epsilon. That means it goes to T state or reject state. That means accept state, otherwise reject state. Then what can you say about this problem? Can we say anything? Question is about what? Whether a Turing machine takes more than 481 steps or not. but it is taking only 70 steps. Then I can say that no sir, it won't take more than 481 steps is wrong. Why? This question is about whether a Turing machine takes more than 481 steps on some input. It's not asking about epsilon. Maybe, so here on this input, it may be taking more than 481 steps. Correct? That's fine. Simply by running your Turing machine on only on epsilon, we can't decide. Sometimes we can decide. Sir, when can we decide? Example, let's say your Turing machine is taking 500 steps. After that, let's say it is halting. Then question is what? Is this Turing machine takes more than 481 steps on some input? Yes. On epsilon it is taking more than 481 steps. I can decide. But only not always, correct? What if it takes only 60 steps here? It doesn't mean that this Turing machine won't take more than 481 steps on some input, right? Maybe here it may take. So then what to do? Now simply I ask one question. You ran your Turing machine on epsilon. It took only 60 steps. But question, is there any input on that your Turing machine takes 481 steps or more? Then sir, I try 0. What if it takes only 70 steps? I try 1. What if it takes only 30 steps? I try 0, 0. Same argument. What if it takes only less than 481 steps? Then if your fate is bad, every input whatever you try, it will take very less number of steps, like less than 481 steps. Then you will stop after some time. Sir, I tried 1000 inputs, sir. Every input was taking only less than 481 steps. That means, so there is no input which takes more than 481 steps. Can we decide like that? No, because wherever you stop in this process, all will take less than 481 steps, but suddenly whatever the input you missed, that might take more than 481 steps, and that might surprise you. Okay, so after some point of time, if you stop the processing in this, I'm not telling that you have to follow this method, but this is a danger with this method. So in this method, you are trying some 1000 inputs, everything took very less number of steps. Then you decided, you were tied, and you said, sir, I realized that there is no input on which your Turing machine is taking more than 481 steps. Is absolutely wrong. Whatever you miss, that may take 481 steps and more, correct? So for that, sir, we understood, sir, we have to run this Turing machine on every input. Maybe this procedure requires that, correct? So finally you realize that, so sir, I run on epsilon 0, 1, 0, 0 in the worst case. If because of my procedure, I have to run this Turing machine for all the inputs. All the inputs means infinite inputs. Then you will be busy in the worst case, looping, correct? That's why there is a chance of looping. But be careful. Your procedure is like that. It doesn't mean that so there is no smart technique, correct? So whatever the procedure comes to your mind at this moment, that was asking for infinite loop to check whether a Turing machine takes more than 481 steps on some input, correct? So be careful. By trying in one possibility and saying that, sir, I got infinite loop, that's why it is undecidable, is wrong. Who said? And who is asking you to do this process? No one, right? This is your procedure. So your procedure has, your idea has infinite loop. It doesn't mean that everyone gets same infinite loop, okay? Otherwise, see this problem. You are writing a C program and you intentionally kept infinite loop like this for infinite number of times. You are running some loop. And after that you are sorting. Then someone asked you, what is the time complexity of your sorting? Infinite. Why? Because there is an infinite loop. So this is the best algorithm. No, you don't say that. There may be a procedure where without using this infinite loop we can sort it, right? There are a lot of such sorting algorithms. That's why that is a mistake in your argument. Here also this procedure is taking infinite loop. It doesn't mean that there is no better procedure. But the question is, can we have a better procedure which eventually which eventually gets terminated after some point of time, after finite amount of time, and it tells answer whether the particular Turing machine takes more than 481 steps or not. Okay. For that, think about it. But fortunately we have a solution. That's fine. Okay. So the solution is like this. To understand the solution, first of all, you should understand this step. You have, let's say, one Turing machine M, and you have some input. What you do is you run your Turing machine for inputs of length 481 only, not more than that. At this moment, blindly remember it. What are you doing now? So we are going to run our Turing machine M, simulate that Turing machine M over only inputs of at most 481 length. Okay, so the reason we will see. First of all, let me ask one question. The number of inputs with 481 length will be how many? Can we calculate? Yes. Example, let's say your input alphabet is A comma B. Since we are going to consider strings of length at most 481. Okay, let me ask one question. How many inputs are possible with A comma B with exactly 2 length? Definitely it will be. So how many 2 length strings are possible? AA, AB, BA, BB. That means 2 into 2. 2 to the 4. Similarly, how many 3 length inputs are possible? 2 into 2 into 2. Correct? 8. In that way, so what I want to say is the number of inputs which we are going to consider are at most 481 length. I will tell you the reason for that. So the number of such inputs are only finite, maybe very large number, but the number of strings are only finite. Remember it, finite number of strings we are going to process. Take each and every input. Sir, how to take each and every input? I will tell you. So any Turing machine, remember one thing, using the code, let's say I can write a code for a Turing machine such a way that that Turing machine can take an empty tape. On that empty tape, it can generate all possible strings of length 481 or up to length 481. Such a code we can write. Everyone recall, in C programming, without taking any input directly, can you write a code for generating permutations? Yes, right? Exactly in the same way. So with same kind of logic, we can generate permutations here. That means what? So I am going to design a code now. Finally, first step of that code is it generates all possible strings in the tape. Okay, string 1, string 2. So I show clearly. This is your infinite tape, right? And that first step is generate strings like this. This is a string number 1. After that, string number 2 here. This is string number 1. So automatically your code is generating string 2, then string 3, then string 4, in that way. Okay. Now once it is generated, how much time it will take? Definitely finite amount of time, because only finite strings you are generating, and each string has at most 481 length. Remember it. Now run your Turing machine. Which Turing machine? Which you are going to take as input. So take the Turing machine M into another step. Now simulate this input S1. Simulate this Turing machine M on this input S1. For how many steps? Only 481 steps. After 481 steps, observe, ask Mr. S1, otherwise ask Mr. Turing machine M. Mr. Turing machine M, within that 481 steps, have you ever reached final state or reject state? No. If it won't come to final state or reject state, I can say that on this input your Turing machine is taking more than 481 steps, and stop and say accept. That means what? What is our question? Is there any given a Turing machine, will it take more than 481 steps on some input? Yes, I got some inputs such a way that my Turing machine is taking more than 481 steps. What if it won't take, sir? It takes only 70 steps. After that it halts. Question is there any Turing machine, right? Is there any string, right? Then now run your Turing machine M on S2. Such a way we have to develop our code. So after simulating M on S2, if this also takes only 75 steps, then run S3, run S4. In that way, only run for this finite strings. Are we doing infinite steps? No, because here some steps, here some steps, here some steps, but the number of strings we are going to simulate on under M are finite. So after finite amount of time, so we will be deciding whether any string takes more than 481 steps or not. Now final summary. Run on all the inputs. All the inputs means only inputs of length at most 481. I will tell you the reason for that later. Okay, after that, if any of the string takes more than 481 steps, say that yes, this Turing machine is taking more than 481 steps on some input, and say accept. Otherwise go to reject state. In that way we can design a total Turing machine for this problem. Now students will have lot of questions here. The one immediate question is, sir, everything is fine, but why are you taking only finite inputs? We supposed to run it on infinite, right? Why are you taking only finite? I will tell you the reason for that. Now we'll see this example. What is your doubt is, sir, without checking all possible strings, you checked only strings whose length is less than or equal to 481, and based on that you are deciding it, sir. But what about the strings whose size is greater than 481? You did not check it, sir. Yes, actually you don't really require to check it. If you have to check, if you need to check all possible strings, then sometimes it takes infinite time, so the problem will become undecidable. But here, with checking only these strings whose length is less than or equal to 481, we can answer it. That is a trick here. So why, I will tell you. So why you don't really require a string of length greater than 481, we will see. First we start with case number 1. What is case number 1 is, so I only process these strings, right? So I ran all the strings on a Turing machine M. Okay, now example, let's say there is a input, okay, a small string, and when I simulated M on this string, so within 70 steps, let's say, actually it got halted. Otherwise, assume that, let's say, this Turing machine M on this input, let's say it took more than 481 steps. Okay, try to understand how many steps it took. More than 481. Now read the statement. So we have to check, we have to test whether a Turing machine takes more than 481 steps on some input or not. So in this smaller size of inputs, if you have such kind of case, then do we really require to go for the other cases? Do we really require to see bigger strings? Not required, right? So case number 1 is, if some, let's say that these are all small set. Let me divide the sets into two parts: small set, big set. Okay, this is small set. Now if some string takes more than 481 steps, then you realize that then you don't require to check bigger set, correct? Bigger set is nothing but my intention, all the strings whose length is greater than 481. So you agree, I think, right? Now only case 2 we have to cover. What is that? What, sir? What if it is case 2? What is that? What is case number 1? Some string takes more than 481 steps, correct? So now what if no string takes 481 steps? We will see. That means all your strings are taking less than 481 steps. Taking less than 481 steps means what? Taking less than or equal to 481 steps means, so before, maybe after 20 steps or 30 steps, they are going to T state or R state. Then only we'll get the clarity about, Turing machine's acceptance or rejectance, correct? So that means maybe it is not taking more than 481 steps, means before that itself final state has been reached or reject state has been reached. Very important property of your Turing machine. What is that? Once you reach a final state, then you will be in final state. That's why Turing machine will be automatically stopped. Once you reach reject state, automatically your Turing machine will be stopped. Example, after 20 steps, if you reach to reject state, then Turing machine is not really required to run further steps. We don't run it. That means we say that Turing machine has been halted after 20 steps. Similarly, after 30 steps, if your Turing machine goes to final state, exactly at 30th step, if your Turing machine goes to final state, after that it will be there only, it will stay there only. Then we say that kind of Turing machine has run for exactly 30 steps. Understand? Now who is required to run for more than 481 steps? If they don't halt, that means if they don't go to T state or R state, that means final state or reject state. Remember it. Now here case number 2 is nothing but, recall case number 1, some string takes more than 481 steps. What if no string takes more than 481 steps in smaller set? Then definitely we have to go for bigger set. But here also you don't require to go for bigger set. Why? See the reason: all possible strings of length less than or equal to 481 halted before 481 steps. That is what finally you realized, right? They are not taking more than 481 steps means what? They got halt before that number of steps. Maybe 20-30 steps. After 20-30 steps, everyone is halting. Remember that point. Now, sir, still our question is, why are you not trying a very big length string? I will tell you. Example, this is a 500 length string. I did not try that. Let me divide into two parts. 481, 19. Okay. Now here you have some input. Let's call A, B something. Okay. Now what I want to say is your Turing machine starts here, correct? Control. Then this input is familiar for you. For your Turing machine, this input, if you focus only up to this point, this part of the input is nothing but already we checked, correct? Try to understand, because if you assume that your input is only up to this point, this input is already examined under Turing machine. When you execute this input ABC, AB something, BA, BB, this part already examined, correct? Why? Because there is one string like this one on which we already executed our Turing machine, that belongs to smaller set. Then on that what happened? On that definitely your Turing machine got halt. That means it went to final state or reject state. Once it goes to final state or reject state, then after further seeing the symbols also, it will be in the same state. That's why though you have very lengthy string here, before that itself, before observing this 481 cells, already your Turing machine got final state, otherwise reject state. How do you know that? That is what case number 2. Correct. So that's why I can say that, however, in the case number 2, by observing this input, that means this, though it has very big length, but by seeing this partial input itself, your Turing machine is going to TRR. Then you don't really require to see the other input before that itself. So finally you are getting the result. That means you are understanding that. So this Turing machine is going to be halt before 481 steps, correct? So that's why in case number 2 also you don't require to check. No need of checking bigger set. Don't worry, I will summarize it. No need to check bigger set. Ready? Let's summarize. Case number 1. In the case number 1, why I am not checking bigger set? Because if some string takes more than 481 steps, that is case number 1. You have this smaller set, and among that one string already taking more than 481 steps, then already, so we solve the problem, then we don't require to check it. Now the second case is opposite. That means first case is not arising. What is first case? Some string is taking more than 481 steps. Then second case is no string is taking more than 481 steps. That means all the strings which are less than 481 length, they are when you run the Turing machine on them, they are going to final or reject. Then why I am not seeing this bigger input is, in bigger input also there is a smaller input. See, every Turing machine will start here, and first it starts here and it will go to right side. So your Turing machine is not jumping to directly to this step, right? For that, first it has to process like this. It is like processing this 481 steps first, correct? 481 bits first. So finally what I want to say is, when you are running a bigger string, actually you don't require to run the bigger string, because we want to run bigger string only in case number 2. Case number 1 is done, forget about that. In case number 2, what is going to happen is, you have already all smaller strings. We tried all possible smaller inputs, correct? So all that smaller inputs were taking less than 481 steps. That means before that itself they are going to either final state or reject state. You remember it. Okay, so that is very important point. Now come to bigger string. What is your question is, sir, if all the smaller inputs fail the case, that means if they take less than or equal to 481 steps, don't we need to check a bigger input? That is what your question, right? You don't really require. The reason is, example, let's say this is a string of 500 cells, otherwise 500 size. So 500 size input will have initially some 481 size input followed by some 19 size input. In that way we can split, correct? Now what I want to say is, so this 481 portion, that input is already examined. Such kind of strings are examined. Now let me tell you one thing. Initially, when your Turing machine was processing this string, it exactly behaves like it is processing like a smaller string. Because what is the difference at this moment? There is no difference. In the smaller string itself there is a, in bigger string also there is a. This is common, right? So that's why behavior will be same. That means it's like, for some point of time, for at least some point, up to some point of time, your Turing machine behaves like it is executing a smaller string, correct? Now When it will change its behavior is whenever it sees a new symbol which it did not see in the smaller inputs, correct? But to come to new symbol, where is the new symbol? These are all old symbols already. Your Turing machine has been examined them in the smaller strings, correct? So the difference comes only when a new symbol, that means a symbol which is I can say which is a part of this 19 cells comes, right? Example, there is a symbol, your Turing machine is processing here, but to come to this point, definitely your Turing machine requires more than 481 steps. The reason, initially your Turing machine is here, it should go right. Whenever your Turing machine makes one right, that means it takes one right, it is one step. So after 481 steps only it will come here. That means what? So definitely before that itself it already processed this string, correct? But what is the result for this string? When your Turing machine is processing this string, already it went to T state or R state. That is what I want to claim. Okay, that is a problem. To process a bigger string, first it has to definitely process the smaller string, but for smaller string what happened, already your Turing machine went to T state or R state before 481 steps. Then only it is case number 2. In that case, when it is already went to T state or R state, then it will not change its state. So after that also it will continue that state. So that's why still you don't really require to check the bigger string in any case. So we don't really require to process bigger strings, only we have to process strings up to less than or equal to 481 size. So that's why what I want to say is, so the number of such possibilities are finite. That means we can easily decide it. How? We will see now. So finally we are running on only strings of length less than or equal to 481. They are finite in number, whatever may be the number. Second thing, and on each input we are running for at most 481 steps to take the decision, correct? So finally the number of steps overall, if you see, they are limited, maybe 1 crore or 5 crores, whatever. But after some point of time we will be knowing the answer. So always we can say yes or no. That's why we can always have a total Turing machine. So this problem is decidable. Now we'll see the D, a Turing machine which takes more than 481 steps on all inputs. Same problem, right? So rather than some input, this time all inputs. Now again you take only, because we understood the logic that, so only take the strings of length less than or equal to 481 first. Then run your logic. That means simulate your Turing machine M on each and every string. Okay. What is our question? Will it take more than 481 steps or not? So now I am taking the strings one by one. String number 1, epsilon. Since its length is less than or equal to 481, I simulate my given Turing machine. Mr. Turing machine M, how many steps you take on epsilon? Okay, if sir I take only 50 steps, that is what this epsilon said. If this epsilon says only 50, but what is our question? Given a Turing machine which takes more than 481 steps or not, right? On all inputs. No, it is not taking more than 481 steps on all inputs, because epsilon itself failed. So we can stop and we can go to reject. That means this is your total Turing machine construction. If so, what you do is simulate your Turing machine on each and every input. Any input stops running, otherwise halts with less than 481 steps, then stop and reject the Turing machine by saying that all inputs are not taking more than 481 steps. If all the inputs takes more than 481 steps, then go to accept state. In that way we can have a total Turing machine. Here also there is no loop, correct? So only when you process infinite strings, otherwise on a particular input if you run forever, then only there is a chance of looping. But here there is no looping, because the strings are limited, and on each string we are going to take the decision after 481 steps. After 481 steps you don't really require to run your Turing machine, right? So that's why all these problems are decidable. Okay, so try to understand whatever I'm teaching. So blindly learn something from these lectures, so that when a new problem comes, that problem will be similar to these problems. Don't worry. So now I know that these problems are difficult. Okay, decidability topic itself is very difficult and confusing, because it requires a strong mathematical foundation. But if you attend my lectures, then definitely your logic will be improved. Okay, so if you improve your logic, then that will help you in solving other questions also. That's why, though you understand, or if you don't understand also, you try to watch the lectures. Second thing, if you don't understand 100%, try to understand 90%, try to understand 80%. Sir, I'm able to understand only 10%. Repeat the lecture if you have time. If you don't have time, let's say, so tomorrow, otherwise within a week you are going to write an exam, don't watch these lectures, because so this requires strong mathematical foundation and you need patience and you need time. If you don't give time, don't watch lectures. If you watch lectures also, understand whatever you can, but don't worry about if you don't understand, don't worry. Okay, so that is the intention now, because decidability is very difficult topic now. So we are going to see some more problems, we will see.